So hello everyone and welcome to today's class. Today we are looking at simple linear regression model. And when we talk about simple linear regression model, we talk about a regression model which consists of only two variables which have a straight line kind of relationship, or which have a linear relationship. And we shall start by saying that consider two variables. Let's consider two variables. We can say two observable variables, x and y, Then the equation given by yi is equal to beta naught plus beta 1 of xi plus ui. Let's call this equation, because this is a continuation from where we stopped last week. So call this one equation number 5. So this equation is called a simple linear regression model. So this is what you're calling a simple linear regression model, where the variable y is called the dependent variable, and then x is the independent variable. Then beta naught and beta 1 are called the regression coefficients. Sometimes we prefer to call them parameters or coefficients. Okay, and we note that the regression coefficients are always unknown. These are regression parameters, just like we have come across the term parameter in the context of other summary values. Just like any other parameter, beta naught and beta 1 are always unknown. Beta naught and beta 1 are always unknown. So if they are always unknown, our business will be to estimate them using sample data. Okay, so that will be our task here. Then u, or what you're calling ui there, u is the error term, also known as the residual term. And we say that the error term or the residual term is usually a combination of a number of effects. So the error term is a combination of several effects, some of them including things like, so the error term comprises of things like the omitted, if you omit some variables, if you have omitted some variables in the model, then the effect of the omitted variables will be lumped up in the error term. Okay, then the error term also accounts for non-linearities. So this one captures, also the error term captures non-linearities. As mentioned up there, this is a linear function. This is a straight line. Okay, so but if the relationship between x and y is actually not linear, if the relationship between x and y is actually not linear, but we end up fitting a linear model, then the nonlinear effect of the relationship will be lumped up in the error term, Then we can also say that the error term also comprises of the measurement. It also captures the measurement or observation errors. So when you are recording the data, or when you're collecting the data, you can experience what you call measurement errors, which may be caused by the tools that we are using. Maybe they are not accurate, they are not giving the true measurements, And in all the cases, we'll always be having some measurement errors. It's only that we can always reduce them. So those errors in the measurement of the observations is always captured under the residue or the error term. Okay. Then finally, the error term will also capture what we call random errors. And what you're calling random errors, these are errors which are inherent in all the processes and cannot be controlled. They are like natural kind of errors which are always there. So the random errors can never be eliminated, can never be removed. But number three, the measurement errors can be reduced because they are part of also what we call mistakes. Some mistakes or human errors in the collection of data or recording of data or even in the analysis of data. So all those errors are lumped up in the residual term. Okay, so the error term basically captures all those four items. Okay, so any question there? So let's move on to the OLS method. And the OLS method is one of the various ways of estimating the regression parameters. There are other ways, but the OLS is one of the most popular way of estimating the regression parameters. And usually when you are analyzing bivariate data, the starting point would be for you to come up with a scatter plot like this one. You come up with a scatter plot like this one. Okay. And the purpose of the scatter plot will be to check whether there seems to be a relationship between the two variables x and y. And if there seems to be some relationship, you may want to check the strength of that relationship. And the strength of the relationship between two variables is given through what we call correlation coefficients. So you may want to calculate the correlation coefficients. So if the correlation coefficient is different from 0, or if there is significant correlation or relationship between the two variables, you may want to estimate the cause and effect relationship. You may want to estimate the cause and effect relationship between the variables x and y. And the cause and effect relationship is what we measure or estimate using regression analysis. Regression analysis. So this tells you the effect of changing the independent variable on the dependent variable. So if you change the independent variable, what happens to the dependent variable? That's what we're calling the cause and effect relationship. Okay. So the OLS method attempts to do this, to give a straight line through the points, like this, for instance, in such a way that if you measure the difference between, so this is the predicted, these are the predicted values, and the dots here are the observed values. So the OLS will help us come up with a straight line like this one in such a way that if you measure the vertical distances like that, you measure the vertical distances from the point to the predicted values like that. So those vertical distances are called residuals. Then after you measure, you square them. You square those vertical distances. That means if some of them were negative, they become all positive. So square, and that's where the name, this word square here comes from. So the OLS method gives us a line which minimizes the sum of the square of residuals. If you attempt putting another line, for instance, if you attempt putting a line here, then you measure the vertical distances to the point, then you square. You do that for all the points, then you sum. You will notice that you will get a larger sum of square. You will get a larger sum of the squares. But there's only one line that will give us the minimum sum of squared residuals, okay? And that line is what we call the line of best fit. Line of best fit. So this line, wherever that line cuts the vertical axis, that's what we call the estimator of beta naught. And the slope of that line, the slope is the gradient. The slope of that line is what is given by is estimated by beta 1. Okay, so basically that is the theory behind the OLS method. So before we go to the details, I want us to say this. We say that given the observations, the pairs, the paired observations like that, for I starting from 1 all the way to n, the task of the econometrician, is to estimate the population parameters, beta naught, which is called the intercept parameter, and beta 1, which is called the slope parameter. Of the above equation, of equation 5 above. So that is our task, to estimate the unknown parameters. So in equation 5, let's add these in an optimal way, using sample information. Okay, so let's look at the assumptions of the OLS method of parameter estimation. So let's look at the assumptions of the OLS method, of parameter estimation. And we're going to look at what we call the classical assumptions of the OLS, which I've written down. And the first assumption is that the error term has a mean of 0. And as we mentioned, the mean can only be 0 if the sum of the errors is equal to 0. Okay? And then using the symbols, we can denote that statement as the expected value of UI is equal to 0. The expected value of the UI is equal to 0. Okay. So if you were to sketch that bit, you would have something like this. You'd be having something like this. If this is your 0 line, maybe this is your x-axis, this is your 0, 1, 2, etc. Then this is -1, -2. So we expect the error term, the errors to be revolving around the 0 line here. We expect the errors to be revolving around the 0 line. Such a way that when you sum the positive errors and the negative errors, they give you a 0 or something very close to 0. Usually, practically, it is very unlikely for you to get a 0, but you always get something very close to 0. So these are the individuals, not necessarily x. So this is what we are calling the error term must be equal to 0. Okay. Then the second assumption is that the error term is homoscedastic, and the opposite of homoscedastic is heteroscedastic. And this one, this assumption has something to do with the variance of the error term. And homoscedastic means that the variance of the error term is constant. And we can illustrate that using this diagram here, where these are the errors. Then here we have the individuals here. So if this is your 0 line, assuming that the mean of the error is 0, then using the blue points show that the variance is constant. The variance is constant for all the individuals. But when you use the red dots and the red lines, we notice that the variance, because variance is a measure of dispersion, we notice that the variation is increasing as we move from one individual to another like that. So the red one is what we call heteroscedastic. In that case, we say that the error term in that case is heteroscedastic. And in the blue one, we say that the error term is homoscedastic. So the OLS assumes that the error term is homoscedastic. Then thirdly, is that the error terms are uncorrelated. the error terms are uncorrelated. That means if you pick any pairs of errors, the correlation will always be equal to 0, which is denoted by this. The correlation or the core of ui, comma, uj is equal to 0 for all I not equal to j. That is, if you're not talking about the same error, if you're not talking about the error for the same individual, then the errors must be uncorrelated. The number 4 is that if you take the sum of the square deviations of x minus x bar, then you should always get a positive value. You should always get a positive number. Then finally, number 5 is that the error term is not correlated with the variable x or with the independent variable. Okay, and this is denoted by covariance of ui, comma xi is equal to 0. Okay, so I guess we can recall what is covariance. For instance, the covariance of x and y is some mean, is the summation of x minus x bar multiplied by y minus y bar divided by n minus 1. That's what we call the covariance. And again, just like we saw in the case of the mean, this can only be 0. It can only be 0 when the numerator is 0. It can only be 0 when the numerator is 0. Okay, so those are 5 classical assumptions of the OLS. We shall be adding a 6th one later, later in this course. Okay, so let's look at the goal or the objective of the OLS method. So the goal of the OLS method, and as we mentioned earlier, the objective of the OLS method is to minimize the sum of square due to residuals. So before we get there, let's mention that model number five was up there, is called the population regression function. Population regression function. Okay, then we say that we estimate it. We are estimating because the parameters are always unknown. So we estimate it with the model. We estimate that model with this model here. We estimated with this model yi is equal to, we estimate beta naught. We also estimate beta 1 x, and the error term will also be estimated. So we estimate that model number 5 with this model here. And we are saying that because, so these are 6, because the regression parameters, beta naught and beta 1 are always unknown. They are always unknown. Just like any other parameter, they are always unknown. Okay. Then we say that if you have some data now, so we say for given values of x, so if you have some data on the dependent variable, the estimated value of y, and the estimated value of y is denoted by y hat. That's how we shall be denoting an estimator. So we are putting a hat to indicate an estimate is given by, the estimated value of y is given by, we have y hat. So that y hat means y estimated is equal to beta naught hat. So that is an estimate of beta naught plus an estimate of beta 1 x. We can call this question number 7. So this is how you estimate y. So y is equal to the estimate of beta naught plus beta 1 estimate multiplied by x. Okay, which is called, so number 7 is called the sample regression function. Sample regression function, or SRF. I should have said the other one is PRF, or the fitted line. This is what we commonly call the fitted line. The fitted line. Okay. then we say that from 6 and 7, from equation 6 and 7, is 7, and then from equation number 6 here. So from 6 and 7, the estimated error term, the estimated error or residual, estimated error or residual term is equal to, so we are talking about this guy here. We're talking about this guy here. We're saying that this guy is equal to, if you are to take these items to the right hand side, and you notice that these items are put in a black rectangle. This is what we are calling y hat. So if I take them to the right hand side, I'll be talking about yi minus y hat is equal to the estimate of the error term. So we say that. So the estimated error term or residual is equal to ui estimate. So the estimate of the error is given by yi minus yi estimate, the estimate of y. Hope that is clear. Which you can write as the same as yi minus, if now I work with this information here, instead of y hat, I replace it with beta naught hat and beta 1 hat x. So this is the same as yi minus beta naught hat minus beta 1 hat x, the same. So the residual, the estimate of the residual is given by that. Say, under the above classical assumptions, the above assumptions, the OLS or the ordinary least squares method, the OLS minimizes, and that's where the word least comes from. So the OLS minimizes the sum of square due to residues. Some people will call it the sum of square due to errors. It's the same thing. But here we choose to use the word residual, due to residuals. Which in symbols you can say as sum of square due to residuals, like that. SSR, sum of square due to residuals. So which is as follows here. So under the above assumptions, the OLS will minimize the sum of square due to residuals. And this is what we are calling the sum of square due to residuals. The sum of UI estimate squared. This is the error squared, then its sum is equal to, so the same. So I've squared here, so I also need to square here, which is the same as yi minus beta naught estimate minus beta 1 estimate x square, then you sum. This is a y. So the sum of square tries to minimize this statement here. The sum of square, the OLS method attempts to minimize this expression here. So we can say for convenience, we let the guy on the left-hand side, we let summation of UI estimate squared to be equal to S. Let's just call it S. Let's call it S. Remember, these summations are starting from I is equal to 1 to N, I is equal to 1. So you are summing for all the individuals, like that. Yeah, that's okay. So even these X's should be having I's and so on and so forth. So let the summation of UI hat, or the estimate of U squared, be represented by S. And then we can say that clearly S is a function of, we can look at S as a function of beta naught and beta 1. That's how I want us to look at it. We look at this as a function of beta naught and beta 1, not a function of X. We look at it not a function of x and y, but as a function of beta naught and beta 1. So in this case, beta naught and beta 1 are the variables of interest. Okay. So now we have S. Instead of that guy, we have S is equal to summation of yi minus beta naught hat minus beta 1 hat xi. We have that. So I've replaced this item here with an S. Then I'm returning the right-hand side, which is a function of beta naught and beta 1. So under the OLS method, our objective is to minimize this function. Our objective is to minimize this function. And as we have mentioned here, S is a function of beta naught and beta 1. So when we start differentiating, we'll be differentiating with respect to beta naught. This will be partial derivatives. We take a partial differentiation with respect to beta naught, and then a partial differentiation with respect to beta 1. So we say that this function SSR is minimized by satisfying the following conditions. Okay. So these concepts are covered in, you covered them in your class and in your differentiation class, in your calculus class. So we are saying that for us to obtain the minimum of the given function, we must satisfy these two conditions. And the first order condition states that this being a multivariate function, we say that the first partial derivative of the function S with respect to the regression coefficients, is equal to 0. So we are differentiating with respect to the regression coefficients, and we are saying that that first derivative or first partial derivative is equal to 0. So partial derivative is denoted using this symbol. So the derivative of that function, the partial derivative of S with respect to beta naught, estimate. So if you apply the chain rule, you will observe that once you differentiate that function with respect to beta naught, you will get minus 2 there, and you get summation, then yi minus beta naught estimate minus beta 1 estimate of x. You will get that. So I starting from 1 all the way to n. So this is the first partial derivative of that function up there with respect to S. I mean with respect to beta naught. And we are saying that this one must be equal to 0. The first partial derivative will be equal to 0. So let's call this one equation number 9. Then the first partial derivative of S with respect to beta 1 estimate will be equal to minus 2 summation, and we have yi minus beta naught hat minus beta 1 estimate xi multiplied by, there's an x out there, I is equal to 1 to n. This one must also be equal to 0. So that's what you're calling the first partial derivative with respect to regression coefficients. So let's call this one equation number 10. Then we can open the brackets in equation number 9 and equation number 10. So we say that simplifying 9 and 10, and we do that by opening the brackets. So you notice that we divide by 2 throughout, because we're only working with this part now. We are working with that. And then we're also working with this. You start by dividing by 2 both sides, so by minus 2 both sides. then you are left with the 2 will go away. So simplifying 9 and 10, we obtain these. We obtain summation of yi minus, so we are summing these. We are summing that. Then we also sum this, and we also sum that. These are constant. Beta naught is a constant, but we are summing it n times. When you sum a constant n times, you get n multiplied by that constant. So n beta naught, like that. So this is summing from I is equal to 1 to n. Then the other one will be beta 1 estimate, then summation of xi. Again, I starting from 1 all the way to n. So when you open the brackets in the first scenario, when you open the brackets, this will give you a summation of y. This will give you n beta naught, and this will give you beta 1 estimate multiplied by x. That should be easy to see. Yeah. So let's call this equation number 11. Let's call that one equation number 11. Okay, then if we do the same for equation number 10, if we open the brackets for equation number 10, we'll end up with summation of yi xi minus beta naught estimate summation of xi minus beta 1 estimate summation of xi squared. And then we are summing 1 to n. We are summing from 1 to n. We are summing for all the individuals like that. So we're saying this is all equal to 0. We call this one equation number 12. Equation number 10 and equation number 11 and 12 familiar. Are these two equations familiar? These two. Are they familiar? Okay, so those are the equations called, so those equations, so we obtain, so let's say we obtain that, which is called the normal equations. Those are the normal equations you are using in business statistics to obtain the regression coefficients. So these are equations to be solved. These are linear equations that need to be solved simultaneously. So once you solve these equations simultaneously, that is 11 and 12, you will end up with the values of beta naught and beta 1. Okay, but before we go there, let's check the second order condition. So that was the first order condition. First order condition. Then second order condition. Second order condition. And because we are trying to minimize, so we need to check whether the second partial derivative, gives a positive value. Gives a positive value. If we were maximizing the function, we'd be looking for a negative value. We'll be looking for a negative value. So we can say using equation number 9. So if you use equation number 9 here, we want to differentiate this equation once more with respect to beta naught. We want to differentiate this function with respect to beta naught. And again, we come here and differentiate this function with respect to beta 1 and check whether each one of them is giving us a positive value. So using 9, we shall have the second partial derivative of s, with respect to beta naught will be equal to, there's a minus 2 somewhere. So the minus 2 will remain there. This minus 2 remains there. Then you differentiate. Actually, you can even use 11. I think 11 is even easier. So if you try to differentiate this function here with respect to beta naught, when you differentiate that with respect to beta naught, it becomes 0. When you differentiate this with respect to beta naught, it becomes minus n. Becomes minus n. Then when you differentiate this with respect to beta naught, it goes to 0. So you will have minus 2 here times minus n. We know that n is always a positive number. N, the number of items, the number of observations is always a positive number. then a minus multiplied by a minus will be a positive value. So we are convinced that the second derivative of that function with respect to beta naught gives us a positive value. Then using 9, here I should have said using 11. I think 11 is easier to deal with. Huh? Then using 10, we observe that the second derivative of s with respect to beta 1 will be, you'll have your minus 2 outside. So I'll continue using the first set of equations. So we have this minus 2. Then when you differentiate the remaining terms with respect to beta 1, so when I differentiate this, remember I've opened the bracket here. I've opened the bracket there. So I'll end up with, you can verify this at home. Huh? You'll end up with minus the summation of xi, I mean xi squared, like that. And clearly, this negative and this negative will become a plus. Then this is definitely a positive number. This is definitely a positive number. So we'll end up with a positive value. So that confirms that. So yeah, that confirms that the second partial derivative of the given function s is actually minimum, has been minimized. So we say that in order to find the values of beta naught, in order to find the values of beta naught estimate and beta 1 estimate, which minimizes the function s, we solve the above normal equations. We solve the above normal equations simultaneously. The above normal equations simultaneously to obtain. So when you solve the normal equations, you obtain these equations. Huh? So the process has been, some steps have been skipped here. So beta naught estimate is equal to y bar minus beta 1 estimate multiplied by x bar. So that's how you get beta naught when you solve the normal equations simultaneously. Okay, then the value of beta 1 is given as follows. So we also say that beta 1, so we can call this one equation number 15. Then beta 1 estimate is given by summation of xi minus x bar multiplied by yi minus y bar, I is equal to 1 all the way to n, divided by summation of xi minus x bar squared, of course I starting from 1 all the way to n. So this is equation number 16. So that's the formula that we use to obtain the values of beta naught and beta 1. Okay, so where x bar is the arithmetic mean of x. So it is obtained by you sum x's divided by n. And then you are summing from 1 all the way to n. Then y bar, I prefer to have it like this, is 1 over n summation of yi, I starting from 1 all the way to n. So these are the sample means of x and y respectively. The sample means of x and y respectively. And then beta naught and beta 1 hat are the estimates. They are the estimates of beta naught and beta 1 respectively. So using the OLS method, that's how you estimate the unknown parameters. I want us to have some remarks here. The remarks will be useful when you'll be attempting to prove that these formulae are correct. So the first remark is that if you take summation of x minus x bar multiplied by yi minus y bar for I starting from 1 all the way to n, this is equivalent to summation of xi, yi minus n x bar y bar. I is equal to 1 all the way to n. So this statement will be very useful at some point. So this is equivalent to that. Okay. And then we also have, if you have summation of xi minus x bar for I starting from 1 to n, this is the same as summation of xi squared minus n x bar squared for I starting from 1 all the way to n. So that's our first remark. And then we also remark that using these two statements, we can write these expressions here in different formats. We can write those statements in different formats. And the new format is what will be expected to use when you want to calculate manually the estimates of beta 1 and beta 0. So we note that the slope coefficient beta 1 estimate can be rewritten in terms of sample covariance, in terms of sample covariance of x and y and the sample variance of x. Okay, so let's recall the definition of covariance. So having recalled that, we can now write that beta 1 estimate is equal to the covariance of xy divided by this should be the estimated, the estimate of the covariance divided by the estimated variance of x. Again, these are estimates. So sometimes you can write like these. The estimate like that. Okay, which sometimes we denote as SXY, that's the covariance of x and y, divided by variance of x. The variance of x has a square like that. So these are subscript. The variance of x like that. Okay. Then we can also note that the slope coefficient can also be expressed in terms of correlation coefficient. Can also be expressed in terms of correlation coefficient. Of x and y. So we can have a beta 1 estimate. So basically what we do, we just manipulate this item here. And if you come here and do this, if you multiply this by s of y, divide by s of y, you see you have not changed the original expression. You have not changed. But you can do that, and then you say, so let me write it here. So s xy divided by s x squared. If I take that, I multiply by s of y, divide by s of y, which does not change the original expression, I can also express it as s xy multiplied by s of y. Then down here, I will have s of x multiplied by s of x, that is s of x squared multiplied by s of y. multiplied by s of y, which I can rearrange into s of xy, s of y divided by s of x, s of y, s of x. So I separate the x's like that. Then this item here is a definition of correlation. That's a correlation between x and y. So this is the same as r x of y, then s of y divided by s of x. But we prefer to have it like this: s of y, s of x, r x, y. Hope you can remember the definition of the correlation between the correlation of x and y is given by a covariance of x, y divided by the standard deviation of x multiplied by the standard deviation of y. That's the definition of correlation. So which is what we're noting as that. So you notice that what we have here in the numerator here, this is the covariance. This is covariance, xy. Then this is a standard deviation of x. This is standard deviation of y. So when you take those items, they'll give you R. So you can also rewrite beta 1 estimate in terms of correlation using this formula. So this is the same as beta 1 estimate. Okay, so those are various ways of writing the value of beta 1. I want us to have an example before we close. So let's consider this example. We shall be using the summary values or the summary statistics obtained from Excel, which are given here. So we shall use this information to obtain the value of the estimate of beta 1 and also the estimate of beta 2. So you'll calculate and send me the answers. And once we're done with that, that will mark the end of today's class. So bye for now, but I'll be waiting for the answers from you.